Hello everybody, this presentation is about incorporating crossflow effects into a transitional model coupled with Thespalart-Allmaras. The content of this presentation includes a brief background of transitional model starting from intermittency functions, intermittency equations, the crossflow transition and instability, the definition and application, the benefit of our extension, some benchmarks, and the conclusion. In fact, the main conclusion of the paper is our extension or my model is 25% faster than its predecessors and as accurate as the previous ones. So I start from 1992. There are some turbulence models before this point, but I start from 1992, which is one equation, intermittency transport equation, based on K epsilon. So that's eddy viscosity model has been proposed, not for transitional flows, for round jet, to which reasonably captures the intermittency of turbulent flow. The second one is intermittency, the transport equation for streamwise direction, and the third one is a combination of first two ones. The second one is based on so-called condition advance, and the third one is coupled with SSTK omega, which is a viscosity model, which is a benefit, which is good, sensitive to pressure gradient of the boundary layer, and considers the actually crossflow effects. But the problem with all these three models is they are non-local correlation, and they consider for considering the diffusion from the free stream into boundary layer, they have to integrate whole the way down to the wall. The fourth one, which is a breakthrough proposed between 2006-2009, is the gamma Reynolds theta. Reynolds theta is an equation which is to calculate the diffusion from free stream into the boundary layer. Gamma is intermittency coupled with SSTK omega. So in total you have to solve four equations. This is non-local, based on, in next slide I will go through that. After that, they decided to discard Reynolds theta equation, so they proposed one equation, just gamma equation coupled with SSTK omega. So you have to solve three equations in total. Afterward, in 2017, a zero equation gamma function is proposed coupled with Thespalart-Allmaras. So in total you have to solve just one nu tilde equation. So in fact, how gamma Reynolds theta works, it works based on calculating the shape factor proposed in 2009, shape factor of the boundary layer, which is sensitive to zero pressure gradient, and they, based on some assumptions, they calculate pressure gradient, so they come up with a value for shape factor, and then it decides about the type of the transition. Mainly in actually in engineering application, the popular or the common type of transition is bypass transition, which the H lies in this range, 2.3 to 2.9. So in this range, this correlation is valid. So you don't need to calculate, to integrate a long boundary layer to find momentum thickness. So they correlated Reynolds theta to vorticity Reynolds number. So it becomes locally correlated. So you don't need to any value somewhere else in the domain. But none of in fact that model just considered those four transitions, not crossflow transition. What is crossflow transition or instability is when your pressure gradient is perpendicular to your streamlines. In fact, crossflow instabilities happens that the amount of this instabilities takes over your streamwise crossflow transition will happen, and so in fact avoiding that, not considering that makes huge error in your calculation. You have to consider. In 2012, a group considered cross-flow instabilities coupled with Wilcox K omega, and they calculated omega for crossflow instabilities in crossflow or intermittency in crossflow. They combined it with omega equation. So for considering crossflow instabilities, you had to solve a transport equation. In 2015, very first group of who proposed gamma Reynolds theta equation considered an implicit empirical correlation, and they added it for diffusion term in Reynolds theta equation to consider this type of instabilities. But the problem with this is that's implicit, and you have to solve it iteratively, which makes the whole model unstable, and that's difficult to implement. The BC model, which is the easiest one, is based on function, not an iterative equation. Introduced a function, an exponential function like this, which will be multiplied in the production term of Thespalart-Allmaras equation. When that function is 0, the flow will be laminar. When that function is 1, the flow will be turbulent, or you will lie down in the turbulent zone. The form of the function will be in this form, and this correlation is still valid. That's, in fact, the extension is already available. Extension, just we studied it, and we combined that extension or that criteria with BC model to consider the cross-flow instabilities as well. So that's easily programmable, and the CF extension is easy to manipulate actually. What is the extension? The extension is this fraction. When this in fact this criterion is met, the cross-flow transition will happen. The denominator is critical or transitional critical Reynolds number, and nominator is cross-flow displacement thickness Reynolds number. In fact, the nominator will be calculated based on helicity, and the denominator will be calculated based on this function, which depends on H shape factor. Which is a curve fitting of pressure gradient based on empirical curve fitting, which is a function of pressure gradient. The nominator actually will be calculated based on helicity. When the helicity is 0, the boundary layer will be 2-dimensional. When the helicity is non-zero, the boundary layer will be 3-dimensional. If the criterion is met, as I said before, cross-flow transition will happen, so the simulation will be 25%, at least 25% faster and as accurate as its predecessor. So some benchmarks: this is 126 prolate steroid for in fact reproducing or similar to a aeroplane body fuselage with 5-degree angle of attack, and actually different turbulence models has been added. This is CF over the upper surface of the spheroid. These two lines are fully turbulent SSTK omega and Thespalart-Allmaras, which expectedly don't detect transition at all. These two lines are transitional turbulence model without CF extension, and these three lines are with CF extension. This solid line with dots, with black dots, is my model, which is as accurate as its predecessors. And you see the runtime here is about 120 hours, and this is about 200 hours. CPU hours, which about 30%, even more than 30% more cost efficient. In fact, another thing that will be considered, that's been shown in the literature, that surface roughness will produce instabilities which are very similar to cross-flow instabilities. So that's very reasonable to include such instabilities into very first criterion. So this existing criterion, this existing exponential criterion, which considers surface roughness, is added to the denominator of the criterion that I showed in the previous slides. So like, in fact, with this constant, which h and h0 are in fact the height of the roughness in this case, in this benchmark, these three cases, or these three amounts, the turbulence model will very accurately and very reasonably will predict the place of transition. In fact, the benchmark that I'm going to show you here is flew around an airfoil with 25 degrees swept angle, three roughness effect of highly polished and painted one, and for different Reynolds number, the transition, as Reynolds number increases, the transition moves toward the leading edge. So in fact, this horizontal line is for fully turbulence model, Thespalart-Allmaras and ASTFE omega, and actually they don't detect transition at all. For these three cases, in fact, as roughness increases, the transition for any case will actually will move and then the turbulence model actually predict the place of transition very well and very reasonable. So in fact, I said the conclusion within the presentation, but the model is very easy to implement, as accurate as previous turbulence models, and to at least 25% faster. And another problem is, as long as it doesn't have any equation, any extra equation to be solved, you don't need to introduce another boundary condition and numerical schemes at all. Thank you for your attention. Goodbye.